So we define convexity of a total preorder in this way, and then also strict convexity. Now assume that our preorder has a utility representation. Is a utility function representing our preferences. Then, how this utility function should be in order that the preorder it represents is convex? So the question is, the preorder is convex if and only if U is what? This condition, which defines convexity of the preorder, expressed in terms of the utility function, means U of x greater than or equal to U of I implies U of 1 minus lambda x with lambda between 0 and 1 plus lambda y greater than or equal to U of y, which is the minimum of U of x and U of y. This is quasi-concavity. Okay, so a preorder is convex if and only if U is quasi-concave. So convexity of a preorder is equivalent to quasi-concavity of a utility representation. Interestingly, U is an arbitrary utility representation here. So every utility representation of this preorder is quasi-concave too. So if we have one utility representation which is quasi-concave, every other utility representation would be quasi-concave, because quasi-concavity means an intrinsic property of the preorder, that it is convex. This wouldn't be the case of concavity. You may very often find a concave representation of a convex preorder, but most of the other utility representation would not be concave, but they will always be quasi-concave. Okay, so concavity here is meaningless. So what would be the meaning of U being concave? In terms of the preorder, no meaning. Being concave means that it is quasi-concave, so that the preorder is convex. But you cannot say anything else, because your utility function is not just quasi-concave but concave. You cannot add anything else, because you have a concave utility representation. You make a composition with a strictly convex function, and you still get another representation of the same preferences. But that one is not concave in general. It would be just quasi-concave. So concavity is meaningless here. Is this clear? Similarly, you can prove that this is strictly convex if and only if U is strictly quasi-concave. Well, now let us solve our problem. Which is our problem as consumers? To spend our money as efficiently as possible, not to waste our money. And then we would like to obtain our most preferred commodity bundle subject to our budget constraint. We have a limited amount of money, and with this limited amount of money, how much utility can we obtain? The larger the utility, the better for us is the consumption bundle, okay? So we have a given amount of money in our pocket, and we will take this amount of money as the money unit. Okay, even I have 1 million rupees in my pocket, it's not the case by the way, but even if I have 1 million rupees, I will call this 1 rupee. Okay, so the money unit is 1. This is what we have available for spending. So given a price vector which in producer theory we assume to be strictly positive, now for technical convenience of the results, the way I'm going to present them, we admit prices to be 0. This is unrealistic because nothing is free, but for mathematical convenience, we may accept that. Okay? So we have a price vector, and then which commodity bundles are affordable for us under these prices. So if I want to buy X under these prices, I have to spend the inner product Px. Okay? I'm buying X1 of good 1, and the price for this good is P1, so I spend P1X1 for good 1, P2X2 for good 2, etc. The sum, which is the inner product, is the total cost of commodity bundle X under the price vector P. But I only have 1 rupee to spend. So the commodity bundles I can afford should satisfy this constraint. And I want to obtain the best commodity bundle for me under this constraint. The best one will be the one with the larger value of U. So the consumer utility maximization problem means maximizing U of X subject to this constraint. There are also the implicit constraint that X is non-negative. No need to write it because it's clear as I write U of X because U is only defined on the non-negative ortho. This is the consumer utility maximization problem. Of which we are going to talk for a while, in the same way that in producer theory we spent a lot of time talking about the cost minimization problem. So you will here see similar things, similar in the structure, but quite different. And also some results will not be as nice here as in producer theory, because I don't want to make it nicer. Because if I do it nicer, I will incur in some technicalities which I want to avoid. But it might be possible. I will tell you in due time. Okay, but leaving aside these minor details, you will see very similarities in the treatment of this utility maximization problem with the treatment of the cost minimization problem we saw in producer theory. But things are going to work very differently here. Only the structure reminds us of that structure, but it's not the same at all. So, in producer theory, we had the production function. Now we have a utility function. And then we define the cost minimization problem. Now we define the the consumer utility maximization problem. And then what we immediately did in producer theory was to introduce the cost function, which actually was the optimal value function of the parametric problem consisting of the cost minimization problem. It was a parametric problem because its definition depending on two parameters, y and p. So C of yp was the optimal solution of the problem corresponding to the values y and p of the parameter. So here we are going to do the same. But here we only have one parameter. We could have two if I didn't say that I just have 1 rupee. If I say I have 1 million rupees, then this should be y here and I will have an extra variable. But no need. And the results are more beautiful and more symmetric when you take y equal to 1. So, the optimal value, so this is a parametric problem with a parameter being p. Okay, so the optimal value of this parametric optimization problem is what in economics is called the indirect utility function. Our original utility function is the direct utility function, if you want, and this will be the indirect utility function. We are going to use V, defined on R plus N, which is the space of parameters, P. Now, I mean, here we are going to use all the time R plus N as the set of commodity bundles and as the set of price vectors. Okay, but now we look at R plus N as the set of price vectors. And it goes into R union plus infinity. Notice that I have not assumed anything about U. U is any function. And then so V of P for P in R plus N, price vector, V of P is by definition the optimal value of this problem. Hello, how are you today? You are not. But you are well. Because first I understood that you were not feeling well. Good. Then, since I'm not assuming anything about you, not even upper semi-continuity. I also not assuming that P has strictly positive components. I'm not working on a compact set. I'm not dealing with an upper semi-continuous function, so I have not guaranteed that the supremum is attained. So I have to accept the value plus infinity as a possible value of the indirect utility function. This creates no problem. This is also a utility function, but not on commodity prices, but on price vectors. It is telling me your preferences on supermarkets. Near your home, there are two supermarkets. In one of them, the prices are the vector P1. In the other one, the prices are represented by the vector P2. To which supermarket are you going to shop today? Well, you will compute V of P1 with V of P2. But V of P1 will tell you the largest utility you can obtain in supermarket 1. And V of P2 will tell you the largest utility you will get in supermarket 2. Then if you decide, if you compute and see that V of P1 is greater than V of P2, this means you can use your money more efficiently in the first supermarket than in the second one. So you prefer the first one to the second one. Okay, so it's also representing your preferences, not regarding commodity bundles, but regarding price vectors, or if you want, supermarket. Is this clear? Now, what did we do in producer theory after introducing the cost function? Then I gave a theorem saying production function satisfies 1, 2, 3, 4, 5 properties. Now, I will tell you which are the properties of V. But here, I will depart a little bit from the scheme we followed in producer theory, as I said, for simplicity. V is quasi-convex and non-increasing. I insist that have not used any assumption on U. No matter how crazy are your preferences on markets will not be crazy. They will be quasi-convex and non-increasing. Non-increasing is obvious because if you increase P, because X is non-negative, then this feasible set becomes smaller, then the supremum is smaller, or at most remains the same. So we have increased P, and V of P has decreased, or remained at the same level. So this is non-increasing. But what about convexity? About quasi-convexity, let's compute the level sets. Fix a level, and what is the meaning that X belongs to the lower level set of V of level alpha. This is the set of, sorry, but the argument of V is P, not X, it's better. So this means that, this simply means that V of P is less than or equal to alpha. And this means what? If you look at the definition of V of P, this means that U of X is less than or equal to alpha for every x such that Px is less than or equal to 1. If you pay attention to this conclusion, then you will observe that this shows us that L of V alpha is the intersection over the set of x such that U of x is greater than alpha of the set of P such that Px is strictly greater than 1. Do you agree that this equivalence is telling us that this equality holds? I mean, suppose P is an element here. Then, for every x here, we have this inequality because we cannot have Px less than or equal to 1, because this would imply that U of x is less than or equal to alpha, which is not the case. So this proves this inclusion. Okay? But if we have now P in the right-hand side, then V of P should be less than or equal to alpha, because otherwise, let me see. So suppose x satisfies it's here. This means U of x greater than alpha implies Px greater than 1. The contrapositive of this is Px less than or equal to 1 implies Ux less than or equal to alpha. What is what we are stating here? And this means that V of P is less than or equal to alpha. So V is in the lower level set. Was this clear? Is this clear enough? Okay, then once you accept that this equality holds true, you have the conclusion, but this says that the level set of V, lower level sets, are intersection of open half spaces, well, open half spaces intersection R plus N, but anyway they are convex. R plus N is convex, intersection and open half space is convex, and then we are taking intersection of some such sets. This is convex. And this is true for every level alpha, so our function has convex lower level set, so it is quasi-convex. For every utility function, no matter how strange it is. So here you have that quasi-convex functions appear in a natural way. Again, by accident, you can get sometimes an indirect utility function which is convex. But this would be meaningless, because if you change your initial representation of U, you replace it with some other utility representation of the same preorder, then the indirect utility function in general would fail to be convex. So convex would be meaningless in this context, but quasi-convexity has full meaning. In fact, one could say more, and I said it. I will give you a reference later so that you can find a perfect duality between direct and indirect utility functions with if and only if results, etc. But this should mean, first of all, telling some other things. I will tell you only very briefly now. These are open half spaces. And this is a closed set, but a closed set is also an intersection of open half spaces, closed convex set. And these intersections of open half spaces have a name. And there are papers and even a book on them. These are the so-called evenly convex set. What is an evenly convex set? There are several equivalent definitions. An evenly convex set is a set such that for every outside point, there is a hyperplane to that through that point does not intersect the set. A convex set with this property. Equivalently, it's an intersection of open half spaces. Equivalently, it's an intersection of open convex sets. Then which sets are evenly convex? First of all, evenly convex implies convex. Okay? On the real line, every convex set is evenly convex. In arbitrary dimension, every open convex set is evenly convex. But it's not hard to see that every closed convex set is also evenly convex. Now, if all open sets, open convex and all closed convex, and all one-dimensional convex sets are evenly convex, the question is, are there convex sets which are not evenly convex? The answer is yes, but not in dimension 1. In higher dimension, there are, and I already showed you one here. When we are talking about hemispaces, so the union of and the shape construction can be made in higher dimension. The union of a half plane with a convex set in the boundary, maybe a half line, maybe a point, maybe a segment, but not the whole line or not the empty set. This is convex, but not evenly convex, because given this point, which does not belong to the set, you cannot find any hyperplane, means any line, through it that does not intersect the set. Well, evenly convex sets are important in some applications, in particular here. If you want, in quasi-convex duality, if you want to build a good theory of duality for quasi-convex functions, you have to consider this notion. I already told you that Jean-Pierre Crouzet, the one who is the best by far in quasi-convexity theory, once told me, and he was the first to consider duality for quasi-convex functions. And then he was following the pattern of Rockefeller for convex functions. And in Rockefeller's case, lower semi-continuity played a crucial role. Then Jean-Pierre thought should be the same here, and he succeeded to develop a theory. But it was quite complicated, and he thought this was my mistake, he said, because I should have considered, but this notion was not so popular in those times. Jean-Pierre's thesis in France, he gave me a copy, more than 200 pages, which I read very eagerly, was very interesting, so much that the copy ended up being destroyed, so I asked him to give me a second copy. Okay? Then his thesis is from 1977. And in those times, even convexity already existed, because in fact it was a notion, I think, introduced by Fenchel himself. I'm not sure now. Yeah, Fenchel, in the 50s, but it was not popular. But then when you adapt, let's say, Kruzek's duality theory, considering even convexity, then everything simplifies a lot. And here you have a hint. These level sets are evenly convex because they are intersection of evenly convex sets. But this is just a comment. If I consider evenly quasi-convex, I take into account the fact that this is evenly convex, then I would say V is evenly quasi-convex. But I'm not saying this, because also this would not give enough information. I mean, the fact that I have that strict inequality here allows me to write here evenly quasi-convex if I want, but I don't want to. But I could still write something else, a property which I don't remember now, but I obtained it. Some condition involving limits, which is a consequence of the fact that in these half spaces you have one here. Okay? Well, so now we know that indirect utility functions are always quasi-convex and non-increasing. Similarly to what we did with ghost functions, they satisfy A, B, C, D, E. Now, after I proved A, B, C, D, E, I suppose I don't tell you which is my utility function. I just tell you the indirect utility function. Can you obtain U from V? You didn't respond, but I responded. I said it's impossible. But the most I can say about the hidden utility function is that, look, this means that U of x is less than or equal. So what are the relations between U and P? U of x is less than or equal to V of P whenever Px is less than or equal to 1. Okay? Because V of P is the supremum. I cannot say maximum. I don't know if it is attained or not. Then, what follows from this equality is that the utility function that produced this V is less than or equal to all these V of P for all these P's. So it's less than or equal to the infimum of V of P subject to Px is less than or equal to 1. So now the roles are exchanged. X is given, and in this minimization problem, the variable is P. Then you solve this minimization problem in which the parameter is x, and this is u of x. So this is the most I can say about u. Let's call this u0 of x, u0 of x. This is a real valued function because it's greater than or equal to u of x, which is real. And well, an infimum could be plus infinity if it is the infimum over the empty set. But this is not the empty set because we can take p equals 0. Okay, so this is finite. So this u0 this u0 is a function from r plus n into r plus, and this function is nice as a utility function because it's quasi-concave and non-decreasing. Can you prove this in just one sentence? Not writing anything on the blackboard? It has the same structure as the indirect utility function, but with infimum instead of supremum. So if you have change here, you have minus sup of minus v of p. Minus v of p is like u there. And we saw that we don't need any property on u. So with a minus sign, would be quasi-convex and non-increasing. After we change signs, it's quasi-convex and non-decreasing. Okay, so you didn't tell me your utility function. Maybe you are crazy consumers. You only told me your indirect utility function, and I produced another utility function, which is reasonable. And I will prove you that it induces the same indirect utility function as your original utility function. This sounds very similar to what we did in producer theory. You had a production function. You didn't tell me, but you told me your cost function. And then from your cost functions, I computed another production function which made the same effect as your original production function. So the pattern is very similar. This is a utility function. So compute the associated indirect utility function. V naught, the indirect utility function associated with u naught. We'll prove that they are the same. So we'll compare V with V naught. They are the same, but one of the inequalities is evident. Which one? V less than or equal to V0 or V0 less than or equal to V. So look at the definition of the indirect utility function. If you replace U with U naught, because U naught is larger, you have a larger objective function here, the supremum increases. Do you agree? So the obvious inequality is this one. But we are going to prove very easily that equality holds. So what's the definition of V naught of P? Is the supremum of U naught of X subject to Px less than or equal to 1. But look at the definition of U naught. If Px is less than or equal to 1, then this definition of U naught says that V of P is greater than or equal to the infimum, which is U naught of X. And sorry, the infimum is U naught, not V of P. So every element here is larger than or equal to the infimum, and the infimum is U naught of X. Then all these elements here, all these X satisfy this constraint, and because of that, all of them are less than or equal to V of P. So this is less than or equal to V of P, which we needed to prove. So for every P, we have seen that V of P is less than or equal to V of P is less than or equal to V naught of P for every P. So we have equality. So you didn't tell me your preferences, you are U, but I produced another U, U naught, which is equivalent to yours in the sense that it yields the same indirect utility function. That is to say, if you tell me that your preference is over markets, I cannot decide if you are crazy or not. Because you may have your original crazy utility function, or you may have this one, which is very reasonable. Maybe your preference is that you prefer less to more. This should be not very reasonable. I don't know, every kind of strange behavior, strange preferences are allowed. But this is not true when you look at your preferences with respect to prices, to supermarkets. Okay? So one can say for every strange consumer, for every crazy consumer, there is a very reasonable consumer which has the same preferences regarding prices as the crazy one. Well, so as I said, you will see many similarities in the treatment of this theory compared with the treatment of production theory. In producer theory, we saw, okay, you don't tell me your production function, but I will find another one which is equivalent to yours. But in some cases, I can't deduce your real production function from the cost function. If your production function has good properties, the same here. The same here. Suppose that, this is a theorem, suppose that your utility function is good, quasi-concave, non-decreasing, and upper semi-continuous. This is not good, this is too good, because I could relax upper semi-continuity by writing even quasi-concavity plus a limit condition. Okay, but I want to avoid these technicalities. By the way, I mentioned about evenly convex sets. If you want to learn about them, this is a very interesting class. There is a recent book, 2 or 3 years old, but my friends and colleagues from Alicante, Spain, Miguel Ángel Goberna, Margarita Rodríguez, etc., and there are 4 authors, José Vicente and María Dolores Fajardo. I think I mentioned all of them. With the title Even Convexity. A whole book devoted to evenly convex sets and evenly convex functions. Well, but let us finish with this statement. Then, if your utility function is good enough, then the function I will obtain by my formula from your indirect utility function will be your original utility function. In general, we only know that your utility function is smaller than this one. Okay. Smaller. Yes. So I said, I don't know you are you, but I know that your u is less than or equal to this y naught that I define. Which means, among all the utility functions which give rise to the same indirect utility function, this is the largest, and the largest is quasi-concave and non-decreasing. Well, but now let us prove that under these assumptions, equality holds. So, suppose this inequality is not true at every x. So suppose for some x, one has u of x strictly less than u naught of x. And then take an intermediate alpha between these two numbers. Then the first inequality is saying that x does not belong to the upper level set of u corresponding to alpha. Okay, this should mean u of x greater than or equal to alpha. You have the opposite inequality. Then this set is convex and closed. Because our function is quasi-concave and upper semi-continuous. Then you are already used to this technique. Whenever you have a point not belonging to a closed convex set, you apply separation. Okay, so there exists a vector which I'm going to call P naught in R plus n, and there is a number k such that P naught set is greater than or equal to k for every set in the upper level set, but not for the point that doesn't belong to the upper level set, which is x. Without loss of generality, we can take k equal to 1. Notice that k is positive because the right-hand side is non-negative, inner product of non-negative vectors. So divide all the inequalities by k, and you get a new P naught, which will be the old one divided by k. Okay, so no problem to assume that k is equal to 1. Then, what happens if Z is a point such that P naught Z is less than or equal to 1? I'm going to deal with the indirect utility function, so I have to maximize the utility function subject to this constraint. Okay, so I am considering any feasible point for that set. Then, if well, so sorry, I mean this is true, but I can do it better. So let us first keep our original k. This is a given number, and this is also a given number because p0 and x are given. So we can lower k. And this will a little bit, taking, let's say, the midpoint between the mean between these two numbers, I will get a smaller number, still satisfying this inequality, but then all these inequalities will be satisfied strictly. So, without loss of generality, I can assume that this inequality is also satisfied strictly. And then now it's the right time to say that I can take k equal to 1. But before, I needed to strengthen this inequality. Okay, is this clear? Then, suppose z is such that p not z is less than or equal to 1. Then z is not in this upper level set, because for every z in this upper level set we have the opposite inequality to this one. This means that u of x is strictly less than alpha. But no, I don't understand the next step I wrote here. No, I quite understand it. So then v of p naught, sorry, this is z not x, v of p naught, which is the supremum of all these sets satisfying this inequality, and all these sets satisfy also this inequality, this should be less than or equal to alpha. And this alpha was taking strictly less than u naught of x, which by definition is the infimum of v of p subject to the constraint px less than or equal to 1. So v of p naught is less than this infimum, strictly less, which means that p naught cannot satisfy this constraint. Otherwise, this infimum would be less than or equal to v of p naught. So this means that p naught x is strictly greater than 1, which is a contradiction. So the assumption that ux was less than u naught at x was wrong. So we must have u of x equal u naught of x, so u naught is equal to u. Is this argument clear? So this means if your function is good, quasi-concave and upper semi-continuous, I can deduce it from your utility function by my formula. As a conclusion, if you have two quasi-concave, non-decreasing, and upper semi-continuous utility function that produce the same indirect utility function, they are the same. Because the indirect utility function determines a quasi-concave, non-decreasing, upper semi-continuous function that produces it in a unique way. So you cannot have two different utility functions with these nice properties yielding the same indirect utility function. But I don't have a bijection as I had in the producer theory. Are stronger than needed. Okay, but for our needs, and if you want to know how to do things with weaker assumptions so that look at the paper titled Duality. Direct and indirect utility functions under minimal hypothesis which I published in the Journal of Mathematical Economics year, but it may have been 1990, around. Or 91, 1991, 92. Probably you can check in Google Scholar. Okay. You will find even convexity, and you will find that limit condition, etc. Too technical for this course. I think it's not worth. Now, time for examples. In producer theory, we basically use two examples, Cobb-Douglas and Leontief. Then these examples make also sense in the context of consumer theory. So I'm going to illustrate all these results with a Cobb-Douglas utility function first, and with a Leontief utility function then. Oh, but it's time to stop, so this afternoon we'll do it. Do you have any question about what I have presented so far? No?